So hello guys, I wanted to follow up there on that video there. I kind of really just gave the general synopsis of it, I didn't really go into any physics really, I just kind of went into the debate about it. Basically, anyway, the Big Bang is okay, it started 13.7, give or take a couple of 100 million years. It started as a something smaller than an atom. Something. It was a primordial, infinitesimal, just small. Just like we're talking Planck scale here, but it was so intensely intensified with energy that it went under a process called cosmic inflation, and this was terrorized by Alan Guth. No, he couldn't have terrorized that until they had found the smoking gun for this. They've sent up COBE, which is the Cosmic Observation Background Explorer, and they've sent up the Jesus, this one's difficult to pronounce. The anisotropy probe. The COBE was first. It kind of gave more of a substandard sort of picture of the microwave background radiation of the cosmos, and the anisotropy, the cosmic microwave anisotropy probe gave a really high, clear, like to a scientific eye, it's probably the greatest image for any astrophysicist. Basically, it outlines where the cold spots are and the hot spots are, and showing you where there was a build-up of galaxies and where there was voids. What was strange about the actual the image itself, it was very homogeneous. It was very kind of smooth, and that's where Alan Guth comes into it. He theorized that there was a cosmic inflation, because like we have the same temperature on one side of the galaxy, or the galaxy I should say, the one side of the universe, and on the other side of the universe we have the same temperature. It's very homogeneous, and that shouldn't be the case. There had to be some sort of mechanism behind that allowed that to be the case, and Alan Guth came up with the cosmic inflation. Basically, what the cosmic inflation is that infinitesimal Planck-size scale, highly energized point. We're talking maybe a dimension in space that just all of a sudden grew higher in energy and inflated to the size of a galaxy in Planck time, and from there it inflated to the observable universe that we see today. and this is why the universe is flat, and this is why we have a net energy of zero. And we find that the universe itself is flat. It's when a physicist called Fritz Zwicky, he noticed something back in the 30s. A thing called the dark energy. Its only attributes really is it interferes gravitationally. It can only be detected by gravitational lensing. On the electromagnetic spectrum, it doesn't have any interference with any light or any energy for that matter. Excuse me. But we know it's there because an astronomer, Vera Rubin, and I have a lot of admiration for her because she was a mother of two actually, and she, like myself, was a fanatic for all things cosmos. And she was in her 30s, and she eventually went away, and she fulfilled her dream. And what a story to say, for her to be the one to discover in full fact, with full proof, that dark energy does exist. It's undeniably there, even though we can't see it. How she discovered that was that I suppose the best way I could explain this in an analogy for you is taking our solar system. The sun takes up 99.9% of the mass of the solar system. The planets that are closer to the sun, they orbit the sun much quicker, and the further you go out, the slower the orbits, because Einstein proved that space and time was a fabric. It's like thinking of say a flat sheet spread out, and you put heavy mass in the middle of that sheet. It'll actually cause a warp, a dip within that fabric, and it's the curving that dip creates is what causes the orbits, the perturbations, and obviously as the further you go out, that dip becomes less of a dip, so the stars, she was looking at galaxies, and she noticed that the stars, the same thing applies to a galaxy as a whole. The stars in the middle should be rotating much quicker. She found that the stars on the outside of these galaxies were spinning just as fast. So there must have been a halo of dark energy holding these galaxies together, because if that wasn't there, then they would just these stars would just fly off. It's like this might be a strange analogy, but like if you ever took, say, a wheel of a bike and you spun the wheel slowly and you poured water in it, the water would be on the tire. It would kind of go around with the wheel, but the further you spin the wheel, you'd see the water fly off, and that's what should happen to these galaxies. These stars should fly off, but they're not. They're being held together by something, you know. Just like the dark energy I mentioned in the previous video, that is something that astrophysics and scientists and cosmologists know very little about. Something that's being extensively studied at the moment. So yeah, the Big Bang and the crucial thing about the video that I wanted to just follow up on here is why so many scientists agree with it. It's because, as I said, theories are theories. Some can sound great and they can fit different observations very well, but they found the smoking gun, so to speak, for the Big Bang. As I said, the Big Bang is 13.7, 13.8 billion years old. They calculated that temperature should at this stage, still have a temperature, and they calculated that it should be 3 degrees above absolute zero, and absolute zero is minus 271 degrees. So you'll be talking this Kelvin. You should be talking 3 degrees above that. And when they sent out these the Anisotropy probe, I hope I'm saying that right, and the Quabi probe, this is exactly what they found. And Penzias and Wilson, they weren't actually astronomers or astrophysicists or anything like that. They were actually they were physicists, but they were working for a company called Bell, and they built a radio telescope. They were trying to learn the distance of frequencies that they could use for Bell themselves. And when they built this telescope, this radio telescope, they pointed in the air, and everywhere they pointed the telescope, they kept finding this static everywhere. It was everywhere in the sky. And at the same time, over in MIT, there was actually a legitimate astrophysicist looking for this static, well, maybe they didn't know at the time in what form they would find it, but they were trying to find the temperature, the smoking gun, so to speak, for the Big Bang. And when they learned about Penzias and Wilson's discovery, they maths speaks for the universe. It's the universal language. Mathematically, it all fitted together. And Penzias and Wilson actually won the Nobel Prize for that. They actually found inadvertently the static. They found I suppose when the Big Bang happened, after say maybe 1 billion years, you would have been looking for gamma rays, which is the highest energy source. 13.7, 13.8 billion years later, the radiation source had depleted down to microwaves, and this is what they found. And this was the smoking gun. This was the smoking gun, and basically, this is why it's highly accepted among the scientific community that that the Big Bang happened, that it was created 13.7, 13.8 billion years ago. Next job is figuring out how it's all going to end, but we need to figure out what dark energy and dark matter actually is first, before we can make accurate calculations on that. So that's a little bit more. I might try a bit of a slideshow just into the creation of Earth and the solar system itself, and how that took formation, and the accretion of our solar system at the time, and what was going on back then. And I might try and put a bit of a slideshow there together. I'd say that might be a little bit more interesting. This was just to finish up the fundamentals, the real sort of the how I would say the key elements of where we are today on cosmology. And I hope I'm explaining that as simple as I can, and I hope I'm making sense. I hope you guys understand that, and yeah, but we'll change it up next time, and we'll do something fun, and we'll throw some slideshows, maybe some pictures in there, and I'll explain some later stuff, I suppose. Yeah, but that's me again. Over and out. Good night, God bless.